Hello everyone, so in this lecture we will study about the Ohm's law, resistivity and combination of sets. So first of all we'll see what is the Ohm's law, right? So suppose we have a conductor, or we can say we have a cross section of wire which length is L, cross section is area is A, and we apply a voltage across this cross section and voltage is V. Then there will be current in this wire and that will be from high voltage to low voltage. Suppose this is I. Now if the physical states of this conductor, that means the length and temperature and area of this conductor remains constant, then we can say voltage applied to this conductor is directly proportional to the current flowing this conductor, right? If the physical states, length, area and temperature of this conductor remains constant, then the voltage applied to this conductor is directly proportional to the current flowing this conductor. If we remove the proportionality, then it will be V equals to I into R. R is the proportionality constant and it is called the resistance of wire. And this is Ohm's law. So V equals to IR. V is the voltage applied to the conductor, I is the current flowing in the conductor, R is the resistance of the conductor, right? So this is Ohm's law. Now if we write this formula, this R in terms of length and area, then we know J equals to sigma into E, or we can write J equals to I upon A. Similarly, E equals to V by L, right? So from here we can write I upon A is same as sigma into V equals to I into R from this Ohm's law upon L. If we simplify this, I will be cancelled. Then this will become 1 upon A equals to sigma upon L into R, or we can write R equals to 1 upon, or we can say L upon A into sigma, and we know sigma equals to 1 upon rho, so this becomes rho into L upon A. So the resistance will in terms of L into A will be R equals to rho L upon A. Rho is the resistivity of this conductor, L is the length of the conductor, area, and A is the area of this conductor. So R in terms of L into A will be rho L upon A. Now the unit of resistance, it is ohm. And unit of rho in terms of ohm we can write ohm into meter. Right, and unit of sigma, it will be 1 upon rho, that means 1 upon ohm into meter, or we can write mho per meter, right? So these two relations you have to remember. Now we will solve some questions based on the Ohm's law and this formula R equals to rho L upon A. So this is the statement for Ohm's law. If the physical states, length, temperature, etc. of a conductor remains constant, then the potential difference across an ideal conductor is proportional to the current flowing through it. Now in this question we have asked, find the resistance of a aluminium wire of length 50 cm and cross section is 2 mm square if the resistivity of aluminium is given 2.6 into 10 raised to power minus 8 ohm meter. Now resistance is rho into L upon A. Rho is given and that is in SI unit. L is 50 cm. So this will be 50 upon 100 meter. A is given 2 mm square. So this will be 2 into 10 raised to power minus 3 square meter square. So put the values of rho, L and A and we will find the value of the resistance. Now in this question we are given the resistance of a conductor of length L, cross section A is rho if its length is made twice. So now the length is 2L, cross section area is half, then the new resistance of the conductor will be, so R equals to rho L upon A. Now new resistance will be R1 rho into L1 upon A. Resistivity of a conductor depends on the material and temperature only. It doesn't depend on the length or the area of the conductor. So rho will be same, L is twice and area is half. So it becomes 4 into rho L upon A, that means 4 times of the R. Now we will see limitations of the Ohm's law. Before that, in some questions they gave the radius and radius is doubled or the diameter is doubled or half. Then we will calculate the area and area of a wire. It is like cylinder, so area of this cross section will be pi r square. So depending upon the radius, area will change, and if length also changing, then we'll put the new length and we'll find the new resistance. Now there are some limitations of Ohm's law. From Ohm's law we have seen V equals to IR. That means V is directly proportional to I. That's the Ohm's law. But for some material, the curve between, for ideal materials, V and I should be a straight line, right? But for some material it is not a straight line, it slightly deviates from this straight line and is graphed like this. Similarly for semiconductors, graph between current and voltage is like this. if current is on this axis and voltage in x-axis, then the graph of I and V for semiconductors is like this. We'll study this graph in details in semiconductor chapter. But Ohm's law is not always like V equals to IR. There are some limitations on Ohm's law also. Now resistivity of a metallic conductor. So we have seen R equals to rho L upon A. So rho, we have seen a formula of the rho. What was the sigma? Sigma was n into E square upon m into tau, right? So rho will be the 1 upon sigma. So from here we can say sigma does not depend upon length and area. It will depend on, first of all, material of conductor. Like for copper it will be different, for iron it will be different. And second, temperature of the conductor. Right? Now suppose at temperature T naught, resistivity of wire is rho, and at a high temperature it is rho naught and it is rho, then the relation between rho and rho naught will be rho equals to, rho is the resistivity at temperature T, rho equals to rho naught 1 plus alpha into T minus T naught. Remember this formula. And alpha is here temperature coefficient of resistivity. And unit of this is Kelvin inverse. Right? So now if we see resistivity of metals, so if we see graph of resistivity, then with the temperature the resistivity for conductor metals are conductor, so resistivity of conductor increase with temperature, and graph will be like this. So at lower temperature graph is not a straight line. You can see it is a curved line. It is a curved line. But high temperature it becomes almost a straight line. And for semiconductors resistivity decrease with temperature. So on temperature resistivity for conductors increase and for semiconductor it decrease. So remember this statement also, it can be asked in exam. Now based on this formula, rho equals to rho naught 1 plus alpha delta T, will solve a question. So in this question we are giving the resistance of the platinum wire of a platinum resistance thermometer at the ice point. Ice point means T equals to temperature equals to 0 degree centigrade. So at 0 degree centigrade, resistance of the platinum wire is 5 ohm, and at steam point, that means 100 degree centigrade, resistance is given 5.23 ohm. When the thermometer is inserted in a hot bath of temperature 345.65 degree centigrade, find the resistance of the platinum wire at this temperature. So now temperature is given 345.65 degree centigrade, and resistance, suppose this is R1, this is R2, and this is R3, which we have to calculate. So at a temperature, resistance will be T equals to R into 1 plus alpha into delta T, right? So remember this formula also, and based on this we can calculate at temperature T2 resistance. First of all, so T2, at T2 R equals to, at T1 1 plus alpha delta T. Delta T is here 100 minus 0. So it will be 5.23 equals to 5 1 plus 100 alpha. If we simplify this, then it will become 0.23, not 0.23, yes, 0.23 and 500 alpha. You can simplify this, 5 plus 500 alpha. So alpha will become 0.23 upon 500, right? Now we have to calculate R at temperature this. So RT3 will be R at T1 1 plus alpha, we know temperature will be 345.65 in minus 0, and RT3 will be, RT1 is 5 ohm, 1 plus alpha value is 0.23 upon 500 into 345.65. So calculate this value and we'll find the resistance of the wire at 345.65 degree centigrade, right? So remember this formula, you can easily find the resistance at another temperature using this formula. Now we will see the formula for electrical energy and power. So suppose we have a conductor of length L and cross section area A, and suppose this end is A and this end is B, and now we apply a voltage across this conductor. Suppose the voltage is V, then at end A voltage is VA, and at B if voltage is VB, then the voltage difference will be VA minus VB, right? This is the high voltage end and this is the low voltage end. Now if the charge flowing through this conductor is delta Q in delta T time, then we can write I equals to delta Q upon delta T, and this becomes delta Q upon delta Q equals to I into delta T. Now the change in potential energy will be U final minus U initial. U final will be relation between potential energy and voltage was U equals to Q into E. So this will be delta Q into V B minus delta Q into VA. This becomes delta U equals to delta Q into VB minus VA, and this is minus of V. So this will be minus delta Q into V. So potential energy will be this. If potential energy is this, then, or we can write this minus I into V into delta T. Put the delta Q equals to I into delta T. So change in kinetic energy will be minus of this potential energy. So this will be I into V into delta T. But this is the case when charge or electrons doesn't collide with atoms and ions. But in actually the electrons will collide with atoms and ions. So this kinetic energy will dissipate in a heat form, right? And this energy will dissipate in heat form. That means the work done will be I into V into delta T, and we know power is work done in unit time, right? So this power will be I into V. If we rearrange this equation, then P becomes I into V over V equals to I from Ohm's law. So this is I into R. So this becomes I square into R, and over we can say P equals to I V upon R from Ohm's law into V. So this becomes V square upon R. So we can say power equals to I into V over V square upon R over I square into R. So remember this formula, and remember this formula also. P equals to worked in a unit time, and unit of P will be joule per second. Over watt. Now the reducing losses in power transmission. So we know from power stations, power comes till our house, and we know there will be some devices near our houses, and that change to the voltage of the power, and that is called transformer, right? So there will be some resistance of these wires, and in these resistance power will dissipate. Now how the power dissipation will be very less? So we know the P equals to V into I over I square into R over V square upon R, right? So power dissipation in this, yeah, power loss in these wires will be PC. Suppose it will be V into I, or we can say PC equals to I square into RC. I will be the same. So from here PC equals to value of I we can put from here. So it will be P square upon V square into RC, and we can see PC will be the directly proportional to the square of, not directly, inversely proportional to the square of voltage. That means at high voltage power loss will be less. So the current is transmitted from power station at high voltage, because at high voltage power loss will be minimum. Right. Now we will see combination of resistors. So first of all we will see the series combination of the resistors. In series combination, current through the all resistors will be same. So suppose this is the resistor R1, this is the resistor R2, this is the resistor R3, and this end is AB, or we can say this is B, this is C, this is D. Right. So current in these resistors will be same. Suppose this current is I. If we connect this with a battery of voltage V, so V equals to IR, we know, right? Now if we see for resistor R1, we can write, if this voltage is V1, we can write V1 equals to I into R1, and V1 will be high at point A and low at point B, right? Because current flow from high voltage to low voltage. Now for R2, V2 will be I into R2. For R3 similarly we can write V3 equals to I into R3. So voltage V will be V1 plus V2 plus V3, and this equals to I into R equivalent. V1 equals to I into R1 plus I into R2 plus I into R3. So this becomes R equivalent. I will be the common, so I and I will cancel out, and R equivalent will be R1 plus R2 plus R3. So for series combination, simply we add the resistors and we will find the equivalent resistance. So it will be R1 plus R2 plus R3 and so on. For n resistors we can say till R1. So in series combination of resistors, current will be the same and the equivalent resistance will be sum of individual resistance. So based on this, we'll solve this question. 3 resistors, 2 ohm, 4 ohm and 6 ohm are connected in series. Find the equivalent resistance. So it is very simple question. So we we'll add this resistance and we'll find the equivalent resistance. Now for parallel combination of resistance, in parallel combination of resistance, voltage through all resistors will be same. So in parallel connection, resistance will be like this. So सीरीज कॉम्बिनेशन में हमने देखा कि वन रजिस्टर का एक एंड दूसरे रजिस्टर से ऐड हो रहा है, बट इन पैरेलल कॉम्बिनेशन में इन रजिस्टर्स के सारे एक एंड एक पॉइंट पर होंगे एंड दूसरा एंड एक अदर पॉइंट पर एडेड होंगे. And suppose this is R1, this is R2, this is R3 and this is point A, this is point B. So we can see R1 के across जो voltage होगा that will be VA minus VB if A is at high voltage. R2 के across भी यही voltage होगा, R3 के across भी यही voltage होगा. That means in parallel combination voltage will be the same through all resistors. Suppose if we connect this with a battery of voltage V, then current is I, then we can see from here current will divide in three branches. Suppose this is I1, this is I2, this is I3, then VAB will equal to voltage of this battery. So we can write V equals to I1 into R1 for resistor 1. Similarly, V equals to I2 into R2 for resistor 2, and V equals to I3 upon R3 for resistor 3. And from here we can write, at this point we can write I is divided in three branches. So we can write I equals to I1 plus I2 plus I3, and आगे हम देखेंगे कि this is the Kirchhoff law of current, right? At a node, total outgoing current is equals to total incoming current. This is the Kirchhoff current law and it is based on the charge conservation. So now if we put the value, I will be the voltage upon R equivalent. From Ohm's law we know V equals to I into R. If we replace this with a resistor which is equivalent to this resistor, then this circuit will be like this. This is current I and this is the voltage. Then we can write V equals to I into R equivalent. So we can write I equals to V upon R equivalent, and I will be V upon R1 plus V upon R2 plus V upon R3. This is V upon R3. So if we simplify this, then we will find 1 upon R equivalent equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So for parallel combination, equivalent resistance will be written like this: 1 upon R equivalent will be 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on. If n resistors are connected in parallel combination, then this will become like this. For two resistor, this formula will be 1 upon R equivalent equals to 1 upon R1 plus 1 upon R2. So this becomes R equivalent equals to R1 R2 upon R1 plus R2. Right? Now we will solve this question based on these two combinations, series and parallel combination. We have to find the current I in the circuit. So here is the current I, voltage we are given 2 volt, and this is the combination of resistors. Now we can see this 30 ohm and this 30 ohm are in series combination. So R equivalent of these two will be 30 plus 30 ohms, that means 60 ohm. So now we can redraw this circuit like this. This is 30 ohm and this is 60 ohm. So these two, we can see this is point A and this is point B. So we can see these two resistors are in parallel combination. So R equivalent will be R1 R2 upon R1 plus R2, that means 30 into 60 upon 30 plus 60, that is 90. So it will be 30 plus 60. देखो कैलकुलेशन मिस्टेक ऐसे ही होती है. 30 plus 60, that means 30 into 60 upon 90. So this become 2 ohm. Not 2 ohm, 20 ohm. Right? So current will be V upon R equivalent. V is 2 volt, R equivalent 20, that means 0.1 ampere. So we can calculate or we can simplify the circuit using the parallel and series combination. So similarly in this question we have to find the equivalent resistance and the current also. So we can see these two resistors are in parallel combination. So we'll find the R equivalent of these two resistors. Then R equivalent of these two resistors and this 4 ohm will be in series combination. Then we will find the R equivalent of this 4 ohm and this equivalent of these two resistors. Then we can find the current and equivalent resistance. So equivalent of these two resistance will be 6 into 3 upon 6 plus 3. For two resistors you can remember this formula. So it will be 6 into 3 upon 6 plus 3, that is 9, that is 2 ohm. Now this circuit will become like this. This is 18 volt, current is flowing in this direction. This is 4 ohm and this is 2 ohm. So now the total resistance, our equivalent resistance will be sum of these two, that is 6 ohm. So current we can calculate I equals to 18 by 6, that is 3 ampere. So in this lecture we have calculated power formula. I into V equals to I square into R equals to V square upon R, and series combination resistance R1 plus R2 plus R3 and so on. And for parallel combinations voltage will be the same across all resistors, and R equivalent will be like this: 1 upon R equivalent equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3, like this, right? And we have studied V equals to IR for Ohm's law. We'll change the color, red color ले लेते हैं. So V equals to IR for Ohm's law, and we have studied R equals to rho L upon A. Rho is the resistivity which depends on temperature and material only. And we have seen resistance at a temperature equals to, at a base temperature, 1 plus alpha into change in temperature. Similarly this formula can be written for resistivity also. Right. So now next lecture we will study about combination of cell and electrical devices.